Thank you very much. So this week we shift gears a little bit. Last week we were handling floor functions. This week we are focusing on polynomials. We're going to begin with the MIT 2023 Integration B qualifying test. And before I really begin, I really encourage you guys to subscribe to our channel. Just give us that extra profile. So that we get some traffic. But above it, so we're going to look at all the problems in the qualifying tests in this video that contained polynomials. So we'll begin with problem 4, which was the integral of the product of 1 plus x squared plus x cubed plus x to the power 4 and 1 minus x plus x squared minus x to the power 3 plus x to the power 4. The next problem was problem 5, which was the integral of the binomial coefficient of x and 5 from 0 to 4. Problem number 10 was the integral of all into the bracket 1 minus x cubed plus x minus x squared cubed plus x squared minus 1 cubed minus 3 times 1 minus x squared times x squared minus 1. Then the next problem, problem 11, was the integral of the absolute value minus 1, absolute value minus 1, absolute value minus 1, absolute value all the way until we have 2023 minus 1s. And then problem 14, which was the integral of from 0 to 1 of x squared over 2 minus x plus the square root of 2x over x plus 1. Problem 15, 1 plus 2x to the power 2022 over x plus x to the power 2023. Problem 17, which is the integral of the product of 1 over 1 plus x to the power 2 to the power k from 0 to infinity. And problem 20, which is the integral from minus 3 over 2 to minus half of x to the power 5 plus 5x to the power 4 plus x to the power 3 plus 8x squared plus x. And those were the problems that contained polynomials. So before I begin again, press the button on your lower right to subscribe to our channel. We just need that extra profile and extra visibility to keep our work going. And also for you, you will get notifications when we do solve these questions. Thank you. So this problem, problem number 4, the product of 1 plus x squared plus x cubed plus x to the power 4 and 1 minus x plus x squared minus x cubed plus x to the power 4 is the way I would solve it. I would use geometrical progression series, and the first thing was to express it as the sum of x to the power I from I is equals to 0 to the to 4, and then the second part there would be x minus x to the power j from j is equals to 0 to 4, and then just using the formula for geometrical series, that would be 1 minus x to the power 5 over 1 minus x, and then times 1 plus x to the power 5 over 1 plus x. Now that results into 1 minus x to the power 10 over 1 minus x squared. Then I would quickly do a division. Using long division, and what we do is inside division sign here we have x to the power 10 minus 1. I have multiplied negative 1 both the numerator and the denominator. And so I would shift the highest degree out, and then divided by x squared minus 1. So you multiplied it by x to the power 8, and then you get x to the power 10 minus x to the power 8. Subtract that from x to the power 10 minus 1, you get x to the power 8 minus 1, and then again multiply by x to the power 6 to the divisor, and you get x to the power 8 minus x to the power 6. Subtract that from x to the power 8 minus 1, and you definitely get x to the power 6 minus 1. Multiply that by x to the power 4. You get x to the power 6 minus x to the power 4. Subtract that from x to the power 6 minus 1. You get x to the power 4 minus 1. And then multiply the divisor by x to the power 2. You get x to the power 4 minus x squared. And therefore, you subtract that from x to the power 4 minus 1. You get x squared minus 1, and multiply 1 by the divisor. You get x squared minus 1, and that becomes 0 when you subtract from x squared minus 1. So dividing the two polynomials in the previous integral results in x to the power 8 plus x squared plus x to the power 4 plus x squared plus 1. And so the integral now is the integral of what was obtained after the long division, which is 1 over 9 to the times x to the power 9 plus 1 over 7 x to the power 7 plus 1 over 5 x to the power 5 plus 1 over 3 x to the power 3 plus x plus a constant c. So the next problem is the integral of the binomial coefficient x5 from 0 to 4, and just using the formula of binomial coefficient. So x5 would be x factorial over 5 factorial times x minus 5 factorial, which is the x factorial is the product of x times x minus 1 times x minus 2 times x minus 3 times x minus 4 times x minus 5 all the way to 1 over 5 factorial x minus 5 all the way to 1. So you realize that the x minus 5 all the way to 1 here cancel with what we have in the numerator, and so we are left with 1 over 5 factorial times x minus 1 times x minus 2 times x minus 3 times x minus 4. Therefore, that integral is the same as 1 over 5 factorial times the integral of x times x minus 1 times x minus 2 times x minus 3 times x minus 4 integrated from 0 to 4. So how I would go ahead to solve it is by saying let y is equals to x minus 2, and therefore dy is equals to dx. And so changing the limits: when x is equals to 0, y is equals to negative 2. When x is equals to 4, y is equals to 2. And so substituting the limits there and also the new variable, we get the new integral to be 1 over 5 factorial negative 2 to 2 of y plus 2 plus y plus 1 times y minus 1 times y minus 2. All the way from negative 2 to positive 2. So now, as you can see, our new integral here is very interesting. We have y plus 2, y minus 2. So when you multiply these two, you get x squared minus 4. And then we have y plus 1, and then we have 1 minus y. When you multiply these two together, you get y squared minus 1. So the integral results into 1 over 5 factorial integral of y squared minus 4 times y squared minus 1 times y from negative 2 to positive 2. And then that becomes 1 over 5 factorial. When you multiply these two together, you get y to the power 4 minus y to the power minus 5y squared plus 4 times y. Multiply y through, and you get the integral of y to the power 5 minus 5y cubed plus 4y, and then becomes now 1 over 5 factorial 1 over 6 y squared the power 6 minus 5 to the over 4 y to the power 4 plus 2y squared. Now these y components are even polynomial. This is an entirely even polynomial, so 2 to the power 6 is the same as negative 2 to the power 6. 2 to the power 4 is the same as negative 4 to the power 4. 2 squared is the same as negative 2 squared. So when you subtract this out, they just cancel out, and therefore the answer is 0. So the next problem is the integral of all into bracket 1 minus x to the power 3 plus x minus x squared cubed plus x squared minus 1 cubed minus 3 minus 1 minus 3 times 1 minus x times x minus x squared times x squared minus 1. So, I guess the first thing I would do is play around with the sign here so that they are all in alignment. So I would flip the 1 here around, and so this positive becomes negative. And then here again, I would flip the 1 minus x, the x squared minus 1 around so that you get 1 minus x squared, and that affects the sign in front of 3 here. And this problem, I think, really is testing how fast one can solve it. And so the next phase is to express everything into the most basic polynomial. So for example, x minus x squared, I would factor x out, and so we're left with x cubed times 1 minus x cubed. And then I would factorize this as well, so we get 1 plus x cubed times 1 minus x cubed. And then in here we would also factor x out so that we get 3 times 1 minus x times x minus x squared still. I think I'll have to factor that in the next step, so that we are able to get x cubed. We're able to get x out, and so we have 1 minus x 3 times, and so we have 1 minus x cubed. So factoring out 1 minus x cubed results into now 1 in the bracket here, plus we're left with only x cubed here, minus we are now left with 1 plus x cubed here, plus 3x times 1 minus x. Expanding whatever is in the bracket, so we get 1 plus x cubed minus 1 minus 3x minus 3x squared minus x cubed. So pretty much binomial expansion of what we see here, minus expanding this minus plus 3x plus 3x squared. So as you can see, this negative 3x squared and this positive 3x squared cancel. This negative 3x and this 3x cancel. The positive x cubed here and the negative x cubed cancel. The one positive here and the negative 1 here cancel. And so we essentially just have the integral of 0. So the answer is a constant. Okay. So this problem is very interesting. Problem 11, which is the integral of the absolute value of x minus 1 absolute value minus 1 absolute, and until we have 2023 negative or minus 1s, from negative 2023 to positive 2023. So let's begin by plotting the value of absolute value of x. As you can see, in the negative direction, the absolute value of x is means that y is equals to absolute value of x is positive. Now when we subtract 1, then the 0 value there shifts to negative 1, but the absolute value now becomes positive 1. And what used to be 1 now shifts to 0. So this process, when you continue, you end up having these triangles, because as soon as each value hits 0, they also, and then you subtract the next negative 1, it oscillates back to positive 1. So it does continue in the same way until the initially 2023 value here becomes 0, right? And that's when you would have subtracted 2023 negative 1 from the successive absolute values. And so the integral now is just the area of these small triangles. And because the base straddles across two unit values. So from, for example, negative 2023 all the way to negative 2021. So there are essentially 2023 triangles. And so the integral is essentially the 2023 times the area of each triangle, which is a half times base, which is 2, times 1, which is the height. And so the area is 2023, and that's the answer. So the next problem is the integral of x squared over 2 minus x squared plus the square root of 2x over x plus 1 from 0 to 1. How I would approach that problem is first of all by dividing x squared by 2 minus x, and that results into negative 1 plus 2 over 2 minus x squared plus the square root of 2x plus x plus 1. And so that now gives us three separate integrals, which is the integral of negative 1 plus the integral of 2 over 2x squared plus the integral of 2x plus x plus 1. So we have three separate integrals, and we're going to try and solve them one by one. The integral of negative 1 is easy. That results in x from 0 to 1, which is negative 1. The integral of 2 over 2x squared from 0 to 1, that's a little bit complex, and then we'll see how to try and solve that. So that second integral of 2 over 2 minus x squared could be expressed as 2 over the product of square root of 2 minus x and square root of 2 plus x. And then if you use partial fractions there, is the same as this 2 over 2 square root of 2 over square root of 2 minus x plus 1 over square root of 2 plus x. And so that now means, because the 2's here cancel, is 1 over root 2. This is the same as negative of natural logarithm of square root of 2 minus x absolute values plus log of absolute of square root of 2 plus x. Now we use absolute values because we want to take natural logarithm when whatever is inside the function is defined. And this is from 0 to 1. So going down, it's the same as 1 over square root of 2. This absolute of square root of 2 plus x over absolute of square root of 2 minus x, because we're using just the principle of the laws of logarithm. So when there's a negative, when there's a subtraction, it means you're dividing whatever is inside the log function. And so substituting for 1 and for 0, when it's 1, it results into square root of 2 plus 1 minus, over square root of 2 minus 1, minus, when it's 0, the x's become 0, so it becomes square root of 2 over square root of 2, which is 1. Log of 1 is 0. So essentially we are left with this value here. Now if you multiply the denominator and the numerator by square root of 2 plus 1, this becomes, the denominator becomes 2 square root of 2 squared minus 1, which is 1. Numerator you get square root of 2 plus 1 all squared. And so you take 2 outside because you have a square inside the log function, you can take it to the constant side. And that becomes 2 over root 2 log of root 2 plus 1. Now I decided to take away the absolute value because I assume here I'll be looking at only the positive values. And so multiply root 2 denominator and the numerator. When you multiply root 2 to root 2 here becomes 2, and that cancels with whatever is in the numerator, and so you're left with only the root 2 in the numerator. So it becomes root 2 log of square root of 2 plus 1. So that is the answer of the second integral. Now, So back on the integral of the square root of 2x over x plus 1 from 0 to 1. So we'll begin by saying that let x is equals to tan squared theta, and so dx would be 2 tan theta sec squared theta d theta, and then adjusting for the limits here. When x is equals to 0, theta would be 0, and then when x equals to 1, theta would be pi over 4. So our integral now becomes integral of 2 tan square theta over square theta plus 1 square root times 2 tan theta sec square theta d theta from 0 to pi over 4. So the d theta term, this term here replaces the dx, and then everything else seems straightforward. So this tan square theta plus 1 is the same as sec square theta, and that square root of that would be sec theta, and that would take away one of the sec theta here in the numerator. In the numerator, we're left with just square root of 2 tan theta. So that now results into, by pulling the constants out, 2 square root 2 integral of tan squared theta sec theta from 0 to pi over 4. Now the integral here is has been derived by black pen, red pen. I will leave a link in the description for you to see exactly how this integral is solved, but it's not a very hard integral to solve. But anyway, the answer is now 2 root 2 half sec theta tan theta minus half natural logarithm absolute value of sec theta plus tan theta. Substituting in the limits results into now it results into root 2 sec pi over 4 tan pi over 4 minus natural logarithm sec pi over 4 plus tan pi over 4 minus root 2 sec 0 tan 0 minus log sec 0 tan 0. This sec 0 becomes 1, tan 0 is 0. This sec 0 becomes 1, tan 0 is 0. So log of 1 is 0. So this entire part becomes 0. And now we are left with only the upper limit to focus on, which we'll continue to solve in the next slide. So as we said, the focus would be on the upper limit, and we'll ignore the lower limit, because everything in the lower limit substitution tends to 0. So that becomes root 2 sec pi over 4 is the same as 1 over cosine of pi over 4, which is 1 over root 2, which is root 2, minus log of, again we have sec pi over 4, which is root 2, tan pi over 4 is 1, and again, yeah, pi over 4 here is 1. So it becomes root 2 times square root of 2 minus log of absolute of root 2 plus 1. And so root 2 times root 2 is 2 minus root 2 times log of root 2 plus 1. Now our entire integral of x squared over 2 minus x plus square root of 2x plus 2x over x plus 1 is obviously a combination of the three integrals that we had alluded to, which is -1, 0 to 1, 2 over 2x, 0 to 1, and then square root of 2x plus over x plus 1 from 0 to 1. And we have the blue, green, and purple. And as you've seen, we've derived it as -1 plus now 2 square root of 2 log root 2 plus 1 plus 2 minus square root of 2 log absolute of root 2 plus 1. So yeah, depending on how you look at this root 2, but this is a positive value, so it's the same as this. So these logs cancel out, and then this becomes now 2 minus 1. So the final answer is 1. So the next problem is problem number 15, the integral of 1 plus 2x to the power 2022 over x plus x to the power 2023. So first thing I would do is factorize the denominator so that we have x times 1 plus x to the power 2022, and then express it as a partial fraction formation. And this looks a little bit more complex because when you do partial fraction, the numerator should always be 1 degree less than the denominator polynomial. So for x, a constant a would suffice, but for 1 plus x to the power 2022, you'd have everything from x to the power 2021 all the way to the constant. And we've used b1, b2 all the way to, the subscripting here should have been better, but for simplicity case, we have b0 at the very end here. Now, if you bring everything together again, you see that our constant a is the same as this 1, so a is 1, and then everything else would be 0, and only a plus b1 would be equal to 2. And since we know a to be 1, b1 would be 1. And so that polynomial is the same as, it would be expressed as this partial fractions, 1 over x plus x to the power 2021 over 1 plus 2022. So the integral now becomes the integral of 1 over x plus x to the power 2021 over x, 1 plus x to the power 2022. And as you can see, the first one is the same as natural logarithm of absolute value of x. The second one is the same as 1 over 2022 times log absolute value 1 plus x to the power 222 plus the constant c. And so if you multiply 2022 across and then pulling out the constant here, you have 2022 log the power x plus log 1 plus x the power 2022 absolute. And then taking this up as a power now allows you to combine those two logarithms, and so you have log 2022 plus log of x to the power 2022 plus x to the power 4044, because this times this is twice that, and so yeah. And why I've decided to remove the absolute terms is because this is definitely an even. Negative of value of x would result in a positive value of whatever is in the bracket here. So this is the answer, and yeah. So the next problem here appears like a monstrosity of a problem, but it's actually very simple, which is the integral of the product of 1 plus, or 1 over 1 plus x the power 2 the power k from 0 to infinity. And so by extracting this integral, what really happens is that this is the same as, because the numerators are all the same, it's the same as 1 plus the product of the denominator, as you can see here. Now focusing on that denominator, 1 plus x to the power 2 to the power k, this is the same as 1 minus x to the power 2 to the power k plus 1 over 1 minus x to the power 2 to the power k, such that this numerator, when you use the difference of two squares, you can always have 1 minus x to the power 2 to the power k, and then 1 plus x to the power 2 to the power k, so that the 1 minus x to the power 2k cancel out, so you remain with this. And so what you see here essentially is that this is a telescoping it's a telescoping product, in that if k is equals to 1, you have 1 minus x to the power 2, right? And then in the denominator you have 1 minus x to the power 2k, so 1 minus x. And the second thing is now 1 minus x to the power, so when k is equals to 2, you have is equals to 1, it's 2 to the power 1 plus 1, so you have 4, and then this is 1, and so you have dot 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 to infinity. You realize this value cancel, and this would cancel with the next denominator here. So essentially you are left with as shown there. So you're left with 1 over 1 minus x for the denominator. So this is very important, and this now can be taken back here, right? And so instead of 1 over that cumbersome term there, you just say 1 over 1 minus, 1 over 1 over 1 minus x. And so the answer here is just 1 minus x. Okay. We've simplified this integral now using whatever series manipulation we used previously. Which is the same as integral of 0 to 1 over 1 over 1 over x, and that over 1 minus x, which results into the integral of 1 minus x, which is the same as x, the 1 becomes x when you integrate it, minus x squared over 2, and so we have the limits of 0 and 1, and so it's 1 minus 1 over 2 minus 0 minus 0, so the answer is a half. And this is the answer. What appeared to be a very complicated problem is actually quite simple. The last problem is actually not very complicated. As you can see, it's the integral of x squared, x to the power 5 plus 5x to the power 4 plus 10 to the times x to the power 3 plus 8x squared plus x from negative 3 over 2 to negative half. This is straightforward. So what you do is just go the hard way. I believe what we're testing here is just how fast someone can manipulate these numbers. Personally, my approach would be going the conventional way, just listing out the integrals of these independent values, and then substituting in the limits. And then I'd subtract the numerator, the upper limit from the lower limit into this independently. Since the denominator is the same, I would just bunch that and just focus on the numerator, as you can see here. So for the even terms, it'll be 1 because the negative will just be positive now, and it'll be 1 minus 3 over 6. When the odd term comes in, I flip around the limits because then we have the negative terms taking effect, and so on. And then I could use the difference of squares here to quickly manipulate them, and basic arithmetic, and eventually our answer would be 40 over 6 times 8, which is 5 over 6. Thank you. Again, I would like to encourage you to subscribe to our channel. We do come up with interesting solutions to some of these hard problems. We also do the easy problems and just appreciate the beauty of walking through some of the easy steps. But yeah, I do encourage you very much to subscribe to our channel so that you'll get updates every time we come up with solutions. Thank you.